Hello everyone, my name is Lydia Mahato, student number 10604006. I'll be doing a presentation about alternative energy design of a rural hospital in QwaQwa. Rural hospitals in South Africa face unreliable power outage, and there's also a frequent load shedding. So most hospitals depend on generators. Once power goes out, they use generators as an alternative, which is costly, and it also harms the environment. So in this project, we propose a PV system which is clean and cost effective, and it's also a reliable energy solution. So we'll be our design will include a proper sizing of a solar panel, batteries, inverters to meet our hospital's load demands. So the system aims to reduce cost, improve healthcare reliability, and enhance sustainability. In our introduction, reliable energy is essential for operations such as lighting, such as refrigerators, such as medical equipment. Most hospitals need proper lighting. So if maybe they're performing a surgery and then power goes out, that becomes a major problem. So South African rural hospitals are highly affected by load shedding, and there's also a weak grid infrastructure, and diesel generators are expensive and they cause air pollution. Solar energy offers a sustainable and independent alternative power source. So this project focuses on designing a solar system for a rural hospital in QwaQwa. So the problem that we have is that there's a frequent power interruption, there's a high diesel cost, there's limited grid access, and there's also a need for reliable, affordable, and sustainable energy source to support healthcare operations. The objective of our project is to design a solar-based power system to meet the hospital's energy needs, and also to improve reliability of medical services by reducing dependence on generators and unstable grid. Another objective is to promote sustainability through renewable energy adoption, to ensure scalability, and to enhance energy efficiency and safety through proper system design and protection. Our literature review. During our research, we've seen that using renewable energy in hospitals and clinics is actually productive. It's a success. Most hospitals in other countries like Kenya, India, and Rwanda shows a success in using these renewable energies. And also hybrid system, which is our solar, wind, diesel, provides reliability. But then using solar only systems, it's more economical in most high sun regions, like most regions that receives high sunlight. And also in South Africa, during our research, we've seen that rural solar projects, especially in Limpopo and KwaZulu-Natal, have shown positive results in cost saving and energy stability. There's also accurate system design depending on load profiling and local solar data. And also studies confirm that proper battery sizing and inverter selections are crucial for stable hospital power systems. The theory on low voltage installation. So low voltage DC systems are used for safety and efficiency in our battery banks. So solar panels generate DC power, which is stored in our batteries, and then from the batteries it is converted to a 230 volts AC using an inverter, and then from there it goes to our it's distributed to our hospital. So our key components are charge controller, inverter, batteries, circuit breakers and isolators, and then proper earthing and protection, which are vital to ensure patient and equipment safety. So the methods that we followed during our project, we first started by load assessment. So we identified the daily power needs, the amount of power our lighting needs, our refrigeration needs, our equipment need in our hospital, and then we then went through with the system sizing, which determines the required solar capacity. So after calculating and identifying our daily power needs, we need to determine the capacity of our solar that is required, the capacity of our battery storage, and our inverter rating. And then from there, we selected our components. So we chose efficient panels, the deep cycle batteries, and reliable inverters. And then we did a single line diagram showing all our connections, which I think is on the next slide, that shows all the connections in our hospital, the hospital layout. And then also safety measures, which includes our isolators, grounding, and circuit breakers, which serves as protection for the equipment and for patients and all the workers. Yeah. So this is our line diagram. This is our hospital layout. It shows all the connections, all the sockets, lightings, anything that any load that will be using our energy. So we used AutoCAD to design this line diagram. So yeah, it shows everything from the site layout, the all the connections required, all the load required. Then we went and calculated our voltage drop. So the goal of calculating the voltage drop is to minimize power loss in cables. So we're given the peak load of 5,000 watts, the system voltage of 48 volts DC, and the cable length of 30 meters. So to calculate our current, we use power divided by voltage, which is our 5,000 volts, divided by 48, and then we get our 104 amps. So the current is 104 amps, then the voltage drop is 9.4 V. We used our current, our resistance, our load to get our voltage drop. Then from there we calculated the percentage voltage drop, which was 9.4, the voltage drop that we got divided by 48, the system voltage, and then we multiplied it all by 100 to get the percentage of 19.6 percentage. And then these calculations shows the selection of appropriate thick copper cables to reduce power losses. Then we calculated our daily energy demand. So to calculate this, we summed up all the critical loads, all the important loads basically. So we have 6.6 watts per watt hour plus 32,000 watts hour plus 12,000 watts hour. So our total daily demand is 51 kilowatts hour per day, or 50.6 thousand watts hour per day. So these are the calculations of our daily energy demand and our voltage drop. Then we calculated power ratings of our components. So the component sizing, we started with the battery bank sizing. The required storage from our previous calculations was 51 kilowatt hour per day. So we multiply that. So we were using a 2-day anatomy. So we calculated that with 2 days. So 51 kilowatt hour per day multiplied by 2 days, which is 102 kilowatts hour. Then the design simplified to 10 kilowatts for calculations. So the battery capacity per hour is energy divided by system voltage. The system voltage we were given 48,000. So it's 10,000 kilowatts. 10,000 watt hour divided by 48, which gives us 208. So for our safety factor, we multiply that with 1.2 and then we got 250. So our final specification is 48 and 250 battery bank. And then we therefore calculated our solar PV array sizing. So our panel configuration is 40 panels times 350 watts, which is 14 kilowatts per schools. So daily generation, its capacity plus the amount of hours the solar gets the sun, the times efficiency. So its capacity sun hours times efficiency, which is 14,000 watts times 5 hours daily average times 0.8 of our efficiency. So the energy generated per day is 56 kilowatts hour per day, which meets our 51 kilowatts hour demand, because initially it meets our 51 kilowatts demand. And then our inverter sizing, we have a peak load of 5 kilowatts and the inverter rating is peak load times our safety factor, which is 1.2, which all equals to it's 5,000 watts times 1.25, which is 6.25 kilowatts. So our inverter sizing that's required is 6.25 kilowatts hour. So for our performance, the whole system performance, the simulated system output is 9.725 kilowatts of AC energy per year. So system efficiency, the specific yield was 1.474 kilowatts hour divided by kilowatts per schools for a high performance indicator, and the inverter efficiency was 95%. So the environmental impact, it's carbon dioxide reduction is 9.1 tons per year. So we are reducing our carbon dioxide by 9.1 tons per year, which is equivalent to planting at least 150 trees. So the final system capacity, our PV capacity is 6.6 kilowatts, our inverter is 12 kilowatts, and our battery is 48 to 500 volts. So this is the simulation of a rural hospital power supply system that was simulated using a helioscope. It shows our PV capacity, our inverter capacity, our battery capacity, our efficiency. So our solar panel capacity 6.6 kilowatts, our inverter is 12 kilowatts, our battery is 58 to 500 volts, and efficiency of 95%. So this is the performance summary of 9.724 kilowatts and our 1.474 kilowatts per kilopascal. Yes, this is our simulated results for our rural hospital in Qwaqwa. So in conclusion, this project was successful. It successfully demonstrated that solar energy is important, is essential, reliable, it's cost effective, and it's a reliable solution for rural hospitals in South Africa. It's sustainable, it's viable for rural hospitals. The design ensures reliability, it ensures safety and cost effectiveness. It can operate independently from the grid, and the implementation will improve patient care and support environmental goals. So with careful planning and accurate sizing, solar offers a viable and sustainable lifeline for rural healthcare, ensuring that critical medical services remain stable and patient care significantly improved. I thank you.